if the current source were short-circuited. Now, you could buy one of those, but heaven forbid if you tried to break that wire off to attach it to something, because then it would not be very happy. So current sources are hard to buy in one sense. And you go back to the voltage source. So a voltage source is very happy to be open-circuited, but it does not like to be short-circuited. So this means the current flows no matter what. Well, a short circuit is a zero-valued resistor. So this means that the voltage, in order for B equal to Ri, for to have a positive voltage, let's say, provided by the source, and resistance is whatever it is, it's 0 for a short circuit. Well, to get a number here, this current would have to be infinite to make everything work out. And so voltage sources do not want to be short-circuited. Current sources do not want to be open-circuited. Voltage sources do not want to be short-circuited. Fundamentals of electrical engineering. Okay. Well, let's talk about power and energy. Now, the conservation of energy principle is that the sum of energies consumed or produced in a closed system is a constant. So you can't produce energy from nothing. A closed system means there's nothing going in or out of the system, and whatever energy is inside that closed system is going to be constant for all time. So what is power? Power is the rate of change of energy with time. So that's just a definition. So P is usually measured in watts, and to be consistent with this definition, the energy would be in joules, and time would be in second. So a watt is a joule second, joules per second. But the important thing for here is that the power, the conservation of energy principle, that the energy is a constant, means that in a closed system, the power, total power in that system is 0 at all times. Inside that closed system, there could be parts of it that are producing energy, producing power, but other parts have to consume it. They have to consume that power. So we should look in circuits, and what I'm going to show a little bit later is that this law is obeyed by circuits. Whatever is producing the power is also consuming it somewhere else. That's just the way things have to be. Well, what's the definition of power for a circuit? So, definition: the instantaneous power, the power at time t, that is dissipated by a circuit element, is the voltage times the current at those same times. Now notice the word dissipated. So positive power, if P is greater than 0, that means you're dissipating power. If P of T is less than 0, that means it's producing power. And that's the convention, that's the way you think about it. Go back to the derivative convention for relationship between power and energy. So if power is positive, that means the energy being consumed by the whatever element's going up, so it's consuming. But if it's less than, it's producing. So it's all very consistent. What's interesting is that watts is equal to volts times amperes. So you measure the voltage in volts, the current in amperes, multiply them together, and you'll get the power being dissipated or produced by that circuit element at that time. So let's go through the various elements and see what the power equations are for them. So for a resistor, Well, V equals Ri. You can substitute this into the power formula up here any way you want. And what you get is that the power is either Ri squared or V squared over R, whichever way you want to think about it in terms of voltage or the current. So, one thing to point out, squaring always gives a non-zero, a positive quantity. Cannot be negative. And that means resistors always dissipate power. And that's why the wattage of a resistor is very important to consider, because it's going to dissipate power, and you better have a physical design for a resistor so that it can let the power dissipate freely up to its stated rating. But always dissipate. So resistors dissipate power. So there has to be some other element in the circuit that produces the power that the resistors dissipate. If you look at the capacitor and the inductor, things are a bit more interesting. So I plugged, let's say, the derivative relationship in here and did a little manipulation to show you that the power consumed by a capacitor is related to the derivative of the square of the voltage. So, now the square of a voltage, of course, again, is a positive number. However, its derivative can be both positive and negative. So there are times when a capacitor can actually produce energy, produce power, and there are times when it consumes it. It depends on the nature of V. And the same thing for an inductor. And in fact, the way we think about these are energy storage devices, the inductor and the capacitor. And the capacitor energy is stored in the voltage, and in an inductor, it's stored in the current. These are results, these equations tell you how to calculate the power that's consumed or produced by these various elements. Now, I want to show you how we're going to start thinking about these. So, our fundamental circuit elements are going to be the resistor, the capacitor, and the inductor. We'll use voltage sources a lot. Now, we are going to build systems out of these elements. It's called a circuit. Now, so all of these elements will go into our system. The sources, they're the ones that provide the signal for the input to the system, and will somehow grab a voltage or a current to be the output of the system. So the sources provide the input X. We're going to have to figure out how you build systems out of resistors, inductors, and capacitors in order to accomplish some goal, some relationship between X and Y that you want, and then some voltage or current will be the output. That's what's coming next. We'll try to build real circuits and try to do something useful with them.